Hey everyone, and welcome to The Explainer. Today, we're jumping right into a really fascinating journey into modern organic chemistry. We're going to look closely at the synthesis of p-Bromoacetanilide, and specifically, we're exploring how traditional chemical synthesis is getting a massive eco-friendly upgrade. Seriously, how exactly do chemists safely build the ingredients for your medicine without, completely blowing up the lab? It sounds like an exaggeration, right? But traditionally, organic chemistry has involved some incredibly harsh, highly toxic, and volatile substances. When you're trying to scale up a reaction to produce a global supply of pharmaceutical precursors, you can't just rely on massive vats of fuming, dangerous chemicals without taking on extreme safety risks. So today, we're going to look at a genuinely brilliant workaround that solves this exact problem for one very specific, highly important molecule. But before we get into the process itself, let's ground ourselves in the physical reality of what we're actually making here. Coming in at a molecular weight of exactly 214.06 grams per mole, meet 4-Bromoacetanilide. If you were to order this from a chemical supplier like Sigma-Aldrich right now, it would show up as a 98% pure, white to light beige crystalline solid, with a melting point sitting right around 165 to 169 degrees Celsius. This little molecule is an absolute workhorse in the chemical industry. It features an amide group and a tightly bound bromine atom on a benzene ring. But the big question is, how exactly do we attach that bromine atom precisely where we want it to go?
Okay, let's dive into this. To understand how we make it, we rely on a really fundamental chemical reaction called electrophilic aromatic substitution. Think of our starting molecule, acetanilide, as this benzene ring with a very large, bulky acetamido group attached to it. When we introduce bromine to the mix, that bulky group basically acts like a chemical traffic cop. Because it's physically just so massive, it creates what chemists call steric hindrance. It's essentially a physical barrier blocking the incoming bromine from attaching to the carbon atoms right next door, which we call the ortho positions. Instead, it forces all that chemical traffic directly to the exact opposite side of the ring, the para position. It is a beautiful, naturally occurring barrier that ensures we get exactly the 4-Bromoacetanilide product we need, rather than some messy, chaotic mix of different molecular shapes.
But here is where the story gets a really strong villain versus hero dynamic. The traditional protocol is, frankly, notoriously hazardous. It requires fuming liquid molecular bromine dissolved in glacial acetic acid. And liquid bromine, it's highly volatile, the fumes are deeply toxic, and it causes severe chemical burns. You need intense safety precautions and heavy-duty fume hoods just to handle it. Contrast that villain with our hero, the green protocol. Instead of handling pure, dangerous bromine, chemists just use sodium bromide salt and literally household bleach, sodium hypochlorite. When you mix these completely benign ingredients together, the bleach oxidizes the bromide to create molecular bromine in situ. That just means the dangerous element is generated directly inside the reaction flask exactly when and where it's needed, and it's consumed almost instantly.
And this brilliantly illustrates the elegant, safe problem-solving of green chemistry. It's almost like a recipe. In step 1, you just dissolve your acetanilide starting material and your sodium bromide in a solvent mix of ethanol and acetic acid. Step 2, pop it in an ice bath to carefully control the reaction temperature. Step 3 is the real magic moment. You slowly add the bleach. Boom! The bromine is generated in situ and immediately consumed by the acetanilide in that exact electrophilic aromatic substitution reaction we just talked about. Finally, in step 4, you add a quick mixture of sodium thiosulfate and sodium hydroxide to safely quench any leftover bleach or bromine. It's incredibly efficient, and you completely bypass the need to ever handle fuming toxic liquids. Let's move to and see how this builds out into a complete laboratory workflow. On the left side of the pipeline, we have the synthesis phase, starting with that raw reaction mixture, generating the brominating agent in situ, and then quenching it. But notice the middle step. The crude product literally precipitates out as a solid. You can just vacuum filter it straight out of the liquid. Now, it's not perfectly pure just yet. To get that pristine, 98% pure crystalline solid we talked about at the very beginning, we have to move into the final phase on the right, workup and purification.
Actually, before we purify it, let's look at the real kinetics behind this green reaction. This data is straight from the Oriental Journal of Chemistry, tracking the steady-state principle of this exact bromination process. What we're doing here is measuring the electromotive force, or EMF, over time as the bromine is generated. Look at the 50-second mark. We're at 700 millivolts. But notice what happens right at 350 seconds. That is our inflection point, hitting 722 millivolts.
This precise measurement demonstrates the actual kinetic rate of bromine generation, which researchers pinned down at a steady 7.14 times 10 to the negative 7 molar per second. It just proves that generating it in situ isn't merely safer, it gives us a highly measurable, controlled, and totally predictable release of the reactive agent.
All right, back to our crude, filtered solid. How do we make it perfectly pure? We use a classic, super satisfying technique called recrystallization. This takes advantage of the massive difference in solubility of our product in hot versus cold ethanol. We take that crude, kind of messy solid and dissolve it in just a tiny splash of boiling hot solvent. As that solution slowly cools back down to room temperature and is eventually plunged into an ice bath, the pure 4-Bromoacetanilide molecules lock together into perfect crystals. This effortlessly strips away the impurities, leaving them trapped behind in the cold liquid. And if you happen to have any stubborn colored impurities, a tiny bit of activated charcoal added to the hot mixture acts like a chemical sponge, just soaking them up right before a hot filtration. It yields absolutely pristine, colorless crystals.
So, the crucial point is, why do we care? Why go to all this trouble for this specific molecule? Well, 4-Bromoacetanilide is a massive player in real-world global chemical applications. For starters, it is an excellent substrate for demonstrating the Nobel Prize-winning Suzuki-Miyawara cross-coupling reaction. It's totally essential for Heck reactions. It acts as a vital building block for more complex molecules like 4-acetamido biphenyl, and its structural cousins are heavily involved in synthesizing everyday pharmaceuticals, including analgesics like paracetamol. Without a safe, highly pure, green way to make this fundamental building block, the entire downstream pharmaceutical pipeline becomes vastly more dangerous and way more expensive.
Now, what's really interesting about this is seeing exactly how our green synthesized molecule fits into that grander scheme. This shows the catalytic cycle of the famous Suzuki-Miyawara cross-coupling reaction. Take a look at the bottom left of the cycle. See that Rx molecule entering the process? That X is the exact bromine atom we just spent all this time so carefully attaching in the para position. Using a palladium catalyst, that PD0 you see at the top, this cycle elegantly strips the bromine right off and stitches our molecule together with a phenylboronic acid to form our brand new carbon-carbon bond. Our safely prepared 4-Bromoacetanilide is literally the structural key unlocking this advanced molecular machinery. It's what allows scientists to build the massive, complex drug structures of tomorrow.
Which brings us to a really provocative thought to leave you with today. How many other dangerous industrial processes might be hiding a simple green alternative just waiting to be discovered? I mean, by swapping out fuming, toxic liquid bromine for literally household bleach and a simple salt, chemists completely neutralized a massive laboratory hazard, and they achieved the exact same highly pure crystalline result. It really makes you wonder what other toxic chemical traditions we're going to rewrite next with just a little bit of eco-conscious creativity. Thank you so much for joining me for this explainer. Keep asking brilliant questions, and we'll see you next time.